A process is like a child doing a homework assignment. The child process has a name, its ID, a set of crayons, pencils, and books, its resources, and a to-do list, its code. The attributes of a process are its ID, current priority, memory size, and what files it has opened, just like a child's school badge ID. How loudly they talk, priority, the size of their backpack, memory, and the notebooks they are using, files. The life cycle of a process can be described in 4 phases. New, the child gets the assignment sheet. Ready, the child sits at the desk waiting for the teacher's signal. Running, the child actually writes the answers. Terminated, the child hands in the finished work and goes home. These phases match what the operating system does: create a process, place it in a queue, let the CPU work on it, and finally clean it up. When a process is alive, it can be in one of several states. Imagine a traffic light for our homework doing child. New, red, just created. Ready, green, waiting in line to use the computer. Running, yellow, actually using the CPU. Waiting, blocked, orange, paused because it needs a missing puzzle piece, I/O. The state transition diagram is a picture showing arrows like new to ready to running to waiting to ready to running to terminated. Each arrow represents a change caused by the OS. The OS can also measure how long a process stays in each state. For example, if a process spent 30 milliseconds in ready and 10 milliseconds in running, we can write total time equals T sub new plus T sub ready plus T sub running plus T sub waiting plus T sub terminated. These numbers help the system decide who should get the CPU next. Shorter waiting times mean a happier user. Explanation: every process has a hidden notebook called the process control block, PCB. Think of it as the child's backpack, where the teacher stores all the important info about that child. The core fields inside a PCB are process ID, PID, the child's school number; parent PID, the teacher who assigned the work; program counter, PC, a bookmark showing the next line of the homework to read; CPU registers, the child's temporary notes like a calculator's memory; state, which traffic light color the child is currently showing; priority, how urgent the homework is; memory management info, a map of which pages of the notebook belong to the child; accounting info, total CPU time used, start time, etc. All these pieces let the OS pause the child, remember where they stopped, and later let them continue exactly where they left off. A context switch is the act of the operating system taking the backpack of one child and giving it to another. The operating system must save the current child's program counter, registers, and state into its process control block, then restore the next child's saved values. Imagine the teacher writing down, John was at question 5, had 2 crayons left, and was waiting for the ruler, and then handing the desk to Mary, reading her saved notes to continue her work. The time complexity of a context switch is usually O of 1, because the operating system touches a fixed size set of fields, program counter, few registers. However, if the process uses a large address space, the operating system may need to flush the translation look-aside buffer, adding a small constant overhead. In simple terms, switching is fast and does not depend on how big the homework is. It only depends on the number of items the teacher has to write down. The scheduler is like the classroom manager, who decides which child gets to use the computer next. It looks at each PCB field such as priority, remaining time, slice, and state. In a preemptive system, if a new child with a higher priority arrives, the manager can interrupt the current child, save its PCB, and give the CPU to the higher priority child. In round robin, each child gets a fixed time slice, say 10 milliseconds. After the slice expires, the scheduler saves the current PCB, puts its state back to ready, and picks the next PCB in the circular queue. Select P sub I equals argmax sub I of open brace priority sub I, or time remaining sub I close brace. Thus, the PCB provides all the numbers the scheduler needs to make a fair or fast choice. Every PCB also keeps track of what resources the process owns, just like a child's backpack shows, which crayons, books, and stickers belong to them. The main resource lists are file descriptors, tiny tickets that say I am using the school library book number 7. The PCB holds an array of these tickets. Memory segments, a map of the child's notebook pages text stack heap. The PCB records the start and end addresses. Limits are limit, rules like no more than 5 crayons max file size max CPU time. The OS checks these limits before allowing new resources. If a process tries to open a new file, the OS checks the PCB's file descriptor table for a free slot, assigns it, and updates the table. When the process ends, the OS goes through the PCB and closes every file, frees every memory segment, and returns the tickets to the pool. This bookkeeping prevents a child from stealing other children's crayons or writing on someone else's notebook. The OS must store many PCBs efficiently. Linked list : each PCB points to the next one like a chain of children standing hand in hand. Adding or removing a PCB is cheap O1 if you have the pointer, but looking up a PCB by PID may require walking through the list ON. Hash map or array indexed by PID : imagine a shelf with compartments labeled by the child's school number. Finding a PCB by PID is O1 because you go straight to the right compartment, but the shelf takes more memory, and you must handle collisions if 2 children get the same number, rare because PIDs are unique. The trade-off is between speed of lookup hash map and memory usage or simplicity linked list. Modern kernels often use a combination : a hash table for quick PID lookup plus linked lists for ready queues. A process can contain many threads, each like a smaller worker inside the same child's backpack. The PCB describes things that are shared by all threads in the process: the PID, open files, memory map, and limits. Each thread gets its own thread control block (TCB), which holds the thread-specific data such as its own program counter, register set, stack pointer, and thread state: running, ready, blocked. Think of the process as the family's house: shared kitchen, bathroom, and each thread as a family member with their own bedroom key (TCB). The OS uses the PCB when it needs to move the whole family, for example, swap the entire process out of memory, and it uses the TCB when it schedules an individual member on the CPU. This separation lets multiple threads share resources efficiently while still being scheduled independently.